Okay, shall we get started with the talk? I'd like to welcome Debanjan, who I've known for quite some time. He's a very leading technical person in the area of IP protocols and networking. He's been working in senior technical roles at Tellium, and I believe previously he was doing a lot of the core R&D. More recently has been doing product management. For those of you who don't know what that means, you probably don't want to know. But he's had a wide experience in different aspects of the company. And today we thought, he is here to sort of share some of the experiences in networking with us, and as part of a program that we have to invite more people with networking expertise to work with us. So you might later want, the students here might later want to follow up and talk directly with him on any topic of interest for you.
Thank you. Thank you for the introduction. Well, I now work in product management. I'm not going to get into the details of that, except for that I kind of logged in hundreds of thousands of miles last 1 year actually. But at one point in time, I almost became a professor. When I graduated in 1995, I almost went to Ann Arbor as a faculty, but somebody convinced me to go to industry instead, and I have been in that loop for quite some time now. So today I'm going to talk about resilient IP backbones, and since I know most of the people here are in wireless area, I'm going to give a little bit of overview of Tellium and where, just to explain where I come from and where Tellium actually fits in this IP infrastructure, although we are an optical networking company. So we'll do a little bit of an industry overview, and we'll talk about different alternatives for IP backbone which different service providers are putting together today. And then we'll talk a little bit about traffic routing and planning, and we'll go through some network case studies which are essentially some of the planning work I did with some of our customers like AT&T, Sprint, and some of the international providers. And we'll get into some of the research issues which I guess especially the students here will be very interested in. Now, just to give you an overview of Tellium, Tellium actually is an optical networking company. Although I work there, I'm not really an optical networking, meaning the physical layer optical networking person. I'm more like a protocol and network systems person. To give you an idea of what Tellium does, we have 3 different types of optical switches: Aurora 32, 128, and 512. I mean, what it means is 512 is a 512 by 512 switching system, and this is every port is OC48 or 2.5 Gbps per second. So the total capacity of the switch is about 1.28 terabits per second. This is the largest optical switch probably money can buy if people have money. But what we have seen in recent past, though, this is probably a little bit too big for what traffic demand people have. And our claim to fame really is our software suite. So we have an element management system, we have a network operating system. This is the software which sits on the switch, and this is something I was intimately involved in when I joined Tellium some 3 years back, and we have some very good planning and modeling tools. Our main value proposition is that the switches actually are very intelligent switches. These are not fat and dumb optical switches. So switches can automatically figure out their immediate neighbors, they can figure out the topology, and you can do OC48 or 2.5 Gbps light path provisioning just by point and click. The second value proposition is mesh restoration. If you the way optical networks operate today, especially SONET and SDH, they are all ring-based systems, and that's very expensive, and in the current environment people really cannot afford that. So they are moving towards a mesh-based optical networking system. And mesh restoration, specifically shared mesh restoration, where the backup capacity is actually shared among multiple light paths, is something that can save a lot of money, and that's something Tellium is known for, and that is a protocol actually I developed in Tellium. Now, before I get into IP networking, I think it's probably a good idea to give you an industry overview where things are and where it is heading. Now, the good news is that data traffic is still growing at a healthy rate. I mean, this is through surveys and personal contacts we had in different service providers. Even in 2001, it grew at almost at 100% year over year. and even this year in 2002, it's poised for 85% growth, which is pretty good actually, given that the base is kind of growing. And data traffic has finally surpassed voice traffic volume in North America. And although the numbers are different depending on who you ask, but the outcome is very consistent in that data traffic has surpassed voice traffic. The difference is something which is probably more of a guesswork. The bad.
Do you know what the data traffic is?
It's about 100 petabytes a month.
No, but in other words, what's the application? Is it, or you just don't know? It's just packets.
Yeah, that's just packet. We don't know the breakup. And it's probably possible to find that out, but I don't have that information offhand. The bad news is that it's not a profitable business. And if you are looking for a job this year, you must have seen that personally. And the bandwidth prices are falling at 30% year over year. There is a lot of unused capacity in the network. In many cases, it's probably going at 40%, 50% utilized. And capital spending on networking equipment has fallen 40% from its peak in 2000. And industry can feel it.
One more question.
Yes, go ahead.
Is there a lot of hardware basically in a warehouse someplace still?
Yes.
So C stock or whatever you want to call it is a problem.
There's a lot of inventory.
A lot of inventory from companies going out of business.
No, even people actually bought a lot of things which they could not use. So a lot of service providers have SONET ADMs and routers sitting in their warehouses, which probably will take them through the middle of 2003 at least. Okay. But one thing is very clear is that if this business has to obtain some kind of efficiency, you have to increase the network efficiency through consolidation and better utilization. Today, if you go to service providers like AT&T, they have 3 different data networks, actually 4. So they have an IP network, an ATM network, and 2 friendly layer networks. And there's, the amount of money they have to pour in order to operate those networks is way too high. And that's not only AT&T, it's probably true about most of the other service providers also. So what a lot of people are trying today is to essentially consolidate everything into a single data backbone. And the goal is to, in cases of, say, Cable and Wireless or AT&T or DT, the goal is to create a common IP Mpls backbone and carry all frame relay and ATM traffic over that backbone. And so what that means is that IP is going to be the dominant protocol in future, if there is any doubt about that. And second is that IP backbones have to be a lot more reliable so that mission critical enterprise application can be put on that backbone. And that's why I think it is important to have technologies so that the IP backbone can be more efficient and more reliable than what it is today.
Do you have IPv6 in mind, or it's still old conventional IPv4?
It's still conventional IPv4. IPv6, is happening very slowly, and it's not even clear whether that's going to take off in a big way anytime soon. So, although IP networks are more reliable today than it was a couple of years back, still there are a lot of failures. And this is actually, I have access to some proprietary data, of course, that's difficult to present. So I got this information from a paper which was done by Craig Lobovitz and Ava Ahuja and Farnam Jahanian at the University of Michigan and Merit Laboratories. So over a period of 3 years, they encountered some 6 million outages. Over 50% of that at mean time to failure of 15 days. And over 75% of routes have mean time to failure of 30 days, meaning that every 30 days, at least one of the routes in this 75% of the pool will fail. And that's pretty high. And it's much lower compared to the carrier class availability we are used to in the telephone world or in the optical world. So 30 to 35% routes have more than 99.99% availability. And only 10% of the routes have availability which is below 95%. And compare that to 99.999, that's 5 nines reliability people are used to in the telephone world. That's actually dramatically low. And service can be affected for a long time also. I mean, once something fails, it actually takes a long time to recover from that. Only 30% of the outages are repaired within an hour. 40% of the failures last more than an hour to several days. And routing convergence, I mean, anytime you have a fiber cut or route a failure, IP is supposed to recover that through rerouting traffic around those failure, but in order to do that, it takes sometimes 15 minutes or more. So during that 15 minutes, the network is really, really unstable.
Excuse me, you mentioned 6 million outage. Is it internet-wide or where the 6 million happened?
It's pretty much internet. What they did actually, they looked at all the BGP routes, which is more or less all the internet routes. But they did it in one network, but they had feeds from other routers, of course. So it's the backbone routes essentially. So in order to understand a little bit more that what is the impact of failure on IP and IP routing, let's take a look at the internet routing architecture. What we have here is that it's a collection of what is called autonomous systems, or ASs. So for example, the two clouds there are two autonomous systems. And autonomous systems are typically managed by a service provider or a big enterprise. I mean, for example, this could be a UUNet or MCI WorldCom network. Another one could be AT&T network. It's kind of loosely defined. Doesn't mean that a single company will have a single autonomous system. They might have multiple autonomous systems, but typically they will have a single autonomous system. Now, two of the autonomous systems communicate with each other using BGP, or Border Gateway Protocol. And within one autonomous system, you have OSPF or ISIS. These are essentially protocols known as interior gateway protocols, which distribute routing information throughout an autonomous system. So if there are some inter-domain route failures, that is, if the BGP link between the two routers in two different autonomous systems fails, then all the routes you learn through the peer router has to be withdrawn from the system. So without getting into very much into details of that, that means that if a BGP link fails, you get a lot of updates that a lot of routes are invalid now, and you have to essentially find a new way to route your traffic. And inside an autonomous system where you have protocols like OSPF and ISIS running, if a link or a node fails, it changes a link state trigger, meaning that the routers which are affected by that link failure will broadcast that information throughout the autonomous system. So what I'm trying to get at actually is that if there is a link failure or a node failure, the impact of that is not local. It can affect actually a lot of nodes. It can affect a lot of people over a wide range of networks. Now, how easy it is for a link to fail? Now, typically when you look at the IP layer, we assume the routers are connected through some sort of OC3, OC12, and OC48 links. If you look a little bit deeper, earlier, at least a couple of years back, the backbone routers were connected over SONET rings. So if you look at two routers there, they are connected over a ring where you have a primary path and a backup path. So every link was protected using SONET links, right? And unfortunately, that was very expensive because you can imagine if there is a router in New York, another one in Denver, and if you want to protect it with a primary and a backup link, that can be quite expensive. In many cases, it actually goes through multiple links, and that makes it quite difficult to manage also.
Well, what are the orange boxes?
Those are SONET ADMs, add-drop multiplexers. And they run protocols like UPSR and BLSR for their protection purposes, right? So what happened recently is that a lot of service providers actually moving from that kind of an architecture to one that's showed on the right, especially for their backbone networks, where they connect their routers directly over unprotected WDM links. So you have OC48, that is 2.5 gigabits per second, or OC192, which is 10 gigabit per second, links, unprotected links, connecting the routers in the backbone. And that makes it very cheap. The problem.
What do you mean by unprotected?
Versus, yeah, how and what way is that unprotected compared to the one on the left, the sonnet ring?
So in the sonnet ring, actually, if you look at the two routers on the left-hand side there and the bottom, they're connected by a green link and a red link, right? And on this side here, they're actually connected directly over an unprotected link. There is no backup path at the physical layer.
But can they just do the same thing? Like if one goes out, just routes all the packets through the other branch?
Right. No, they can.
Still have
Actually,
to
they
branch
do
or
some of that. I'll come to that.
So is the notion of a backup route over here some physically just going a path?
That's correct. Yes. That's correct. So if you take a little bit deeper look into how these routers are connected in different POPs, this is a typical architecture in any backbone service provider POP. You have two routers, actually here known as the core routers, and they are just for sake of redundancy. No service providers will actually put one router in the core backbone POP. And then you have a layer of access routers which are connected to those two core routers. And they are kind of, dually interconnected so that if one of the routers fail, they still have connectivity out of that POP or that central office. And then customer routers are connected to the access routers. On the network side, the core routers are connected to other POPs or other point of presence over WDM, typically now with OC192 or 10 Gbps links. Okay. Now, before we get into that, how we can get around failures and how we can make networks more resilient, if you look at different types of failures, you can, there are primarily 4 different types of failures. You have transport failures, in which case you will have essentially the links going down because of fiber cut or WDM failure or an amplifier failure. And they are about 26% of the failures. I mean, this is from some statistics we got from RHK and others. Then you have router failures. Routers are quite prone to failure. And router failures is about 28% of the total failure. One thing we should remember though that most of the router failures are from software failures. So you can do a power cycle and the router can get back up in 15 minutes. If you have a transport layer failure or a link cut or fiber cut, that takes more than 4 hours, sometimes actually days to repair. And then there are network failures, which are typically due to congestion and misconfiguration and sometimes denial of service attacks. You have some maintenance problem, and this typically actually affects only customer routers, not the core backbone router. So the point here is that the transport failures are a big portion of the failures, and if we can make our transport backbone more resilient, you can probably get rid of most of the very bad failures from the network.
What are the impacts of these types of failures?
Yes,
You're coming to that?
Yeah, transport failure especially. So, we talked about the routers in different POPs are connected over WDM system. What typically happens is that these WDM systems are connected back to back, and different routers are connected to the same WDM system. In this particular case, if you look at the router at POP 1, it's connected to POP 2, POP 3, and POP 4 over the same WDM system, the shared WDM system you see here. Sometimes routers in different POPs, in this particular case POP 5 and POP 6, they can share, for example, a common conduit. They are going through the same cable. So, when somebody comes and says that I need a wavelength to connect router from POP 1 to POP 4, you will get a wavelength, but you will have no idea where the wavelength is going through. So, for example, if there is a failure on the shared WDM or on the shared conduit, a single failure can actually take down multiple, 10 gigabit links connecting POP 1 to other POPs. And that happens pretty frequently, actually. If you remember the fire in the Baltimore tunnel, that actually affected a lot of service providers for a long time. So what happens if a link goes down, right, or multiple links go down at the same time? That kind of perturbs your routing. Your OSPF or your IGP will start flooding the network with the link state updates that I have a failed link, and multiple of them will do that. Then your BGP connections might go down, which means that all the routes you learn through that BGP connection, you have to essentially, throw them out, and you have to restart learning that. So there is a big impact, especially when you have large links of 10 gigabit capacity, and multiple of them going down at the same time. That can part out the network for a very long time. But IP layer do have some mechanisms to protect against this kind of failures. And the current mode of operation is essentially rerouting around the failure. So both IGP and BGP, they know how to do the rerouting. The problem with that is that it takes a long time to get to a network convergence when you have a failure of really big magnitude. And if you have applications like voice over IP, which actually picking up slowly, you cannot let your network recover for 15 minutes when you don't have any network connectivity or very poor performance. So there is a new mechanism which people are using for protection at the IP layer, that is the Mpls protection mechanism. This is actually an IP layer mechanism which is very similar to the SONET protection in some sense, but in a mesh architecture, that you have a primary path and you have backup path. You send your traffic over the primary path. Your backup path is pre-established but not carrying any traffic. And when there is a failure, you learn that at the source, and then you switch your traffic from the primary path to the backup path. Right? That is the MPLS end-to-end protection. MPLS end-to-end protection, unfortunately, is not very fast, although it's improving over time. So in order to make it faster than what it is right now, there is another mechanism in MPLS which is known as MPLS fast reroute. So if you call the first one end-to-end protection, this is actually a span protection or a link protection in some sense, where you have multiple backup spans which protect against failure of one or more links. Right? So if you look at the first reroute example on the top picture there, that shows that for every span you have a backup span. And again, problem with so many of those backup spans is that it's a lot of state information and it's a lot of wasted bandwidth. So people have come up with what is known as fast reroute with merged detour example. So there you can merge actually multiple of these backup span by a single backup span. It's not as efficient in terms of switching performance, but it saves bandwidth and it kind of reduces the network state here to keep in the network. The other option, of course, is optical restoration. Taking a state back, essentially, that where we saw that IP routers are connected over SONET rings, and you're getting primary and backup paths there. You can do optical mesh restoration instead of optical ring restoration, which you get from SONET and SDH. And the advantage of doing that is that it can be much cheaper than optical ring restoration, and a lot of people are moving in that direction. Just as an example here, that if you compare ring restoration, this was actually done on a 75 cities network, 93 fiber links, that if you compare the primary and backup capacities required in a ring network and compare that with shared mesh restoration, you can save 52% in terms of number of ports on your switches and on your ADMs. I'm not getting into the details of that. It's kind of a detour from what you want to discuss today. And I'll go over it quite quickly also. That another advantage of optical restoration as opposed to restoration at the IP layer is that it's much more scalable because you are restoring at a much larger chunk. Here you are restoring 2.5 Gbps and 10 Gbps channels instead of MPLS LSPs, which could be a couple of megabits per second. Other thing which is kind of important to note here is that when you do restoration at the optical layer, since it's very close to the fiber plant and the way fibers are routed, you have good information about route diversity. So you know if a particular fiber is going through sharing the same conduit with another fiber, and that information you can use to create primary and backup paths which are truly route diverse. that they are physically route diverse. And that information is not very readily available at the IP layer because we have climbed one layer. So even though theoretically MPLS can provide you a primary and backup path, it's very difficult to figure out whether those primary or backup paths are sharing the common risk or not.
So somehow if one layer lower, that's easy to figure out?
Yeah. Because those two, people managing those two layers typically don't talk to each other.
So is there like sort of what you're calling it the optical layer, which I guess is like is it different? Would you use is that a synonym for the physical layer?
Yes, I mean the fiber, the WDM equipment, and the optical switches all together. I call it optical layer. You can call it physical layer also, and that's typically managed by one organization. And then you have the IP network and the data network managed by a different organization. And they may or may not be in the same service provider network also. I mean, you might be just an IP service provider, and when you ask your physical network provider that provide me with a 10 Gbps link, you will get a 10 Gbps link. You won't get the information associated with which physical path it is taking. It's a 10 Gbps link between two cities.
So in essence, you put the burden on that person to say, I want it with a certain reliability in the way that physical layer provider is going to give that reliability by using optical restoration?
That is correct. That is correct. I mean, although it looks like a simple bureaucratic thing that you can pass on that information to IP layer, it doesn't happen that easily. It can happen, but it doesn't happen. So another advantage of optical layer restoration is that it improves network stability. And let me get into a little bit of details in here. That if you look at restoration of the IP layer, be it MPLS or be it IP rerouting, when something happens on the primary path, the green arrows here, traffic is actually physically rerouted on the backup path, and all the routers have to know about it, which essentially means all your routing tables have to change, right? So anytime there is a failure, there is a turbulence in the network. If you look at optical layer restoration, what happens really that you have a primary link and a backup link. And if something happens on the primary link, it is replaced by a backup link, which is between the same two endpoints as far as IP layer goes, and which is of the same capacity as far as the IP layer goes. So nothing really changes in terms of routing as well as network utilization. So your topology remains the same, your routing remains the same. So the impact on routing when you do restoration at lower level is much lower.
Can I ask a really dopey question?
Sure.
You draw these conceptual pictures where, like, the red dots indicating an optical path going from there to there, right? In these switches, the fact is it isn't a single wavelength that is assigned all the way through, is it? Or
No.
is it?
Actually, most of the switches you have today, they are OEO switches, meaning that they are actually electrical core. You can have an all optical switch, which is still in research labs, and it's not clear whether they will ever be deployed. And you have OEO switches where you get an optical signal, you convert that into electrical signal in the switch, and then convert it back into an optical signal on its way out.
Yeah. So you're just sort of logically
That's
thinking of
correct.
it as
It's not an wavelength really, it's a light path. So it can have different wavelengths on different segments of that path.
calling it a light path makes it really seem like it's it's the same light going all the way through. So, all right.
Okay. Well,
I
you
just
can
wanted
call
to
it
be
a
sure
sonic
what
path
I
or
thought.
whatever. So, what we actually did is try to figure out what is the best physical topology for a given traffic pattern. So most of our customers, say IP customers like say Cable and Wireless or AT&T or WorldCom, they have their IP traffic metrics, that this is the amount of traffic going from this node to this node. And they want to figure out what is the best way of constructing the physical layer so that it will give them the cheapest and the best possible IP network they can have. What we did really is that this is a 12-node IP backbone, which is typical of most of the major US service providers. And if you look at how traffic will be routed when you go from New York, which is on the right-hand side here, to LA on the left-hand side there, it will go through multiple hops. Now, what you can do is that you can create physical layer connection or light paths to create a more meshier network, so that instead of getting on 3 hops from New York to then Cleveland and then to Chicago and then to Denver down there, you can have a physical path between New York and Denver, and then you can ride that physical path with your IP traffic. So the goal was to figure out, given a traffic pattern and given a topology, what is the best network we can build which will make it cheapest for our customers.
Is that Miami down in the lower
Houston.
River?
Which one? This one down in Miami. It's probably might be in the ocean, but that's Miami.
Miami. And that's Houston is the one in the
That's Dallas,
whole Dallas. Okay.
and actually that's San Francisco down there, and then there's LA,
LA
and
is
top
lower.
there is Seattle. And it's kind of surprising that almost all of them kind of have the same topology because they buy fiber from the same guys. These are all level 3 fiber. Well, I don't know how much of details I should get in here in terms of primary and backup routing. If you look at the whole problem here, that you have a physical layer routing to be done, and top of that you have to do an IP layer routing, and you're trying to figure out what is the cheapest network solution you can have, accounting for all your IP layer cost as well as physical layer cost. Without getting into detail, that's a hard problem, which is an NP complete problem. So we came up with some heuristics actually to finding the optimal, or near optimal routing in that scenario. And we compared that with what you can get by doing an ILP formulation of the problem, essentially, doing some crunching using Cplex and see how close you are from that optimal solution. So the results I'm going to present here, without getting into the details of what algorithm we used, is within 10% of what we saw we can get from an ILP formulation. So it's a near optimal result. And the routing problem is kind of very similar in both the physical layer case, where you're trying to find a primary path and a backup path, and Mpls or IP layer case, where also you're trying to find a primary path and a backup path, right? And a couple of points maybe good to mention here is that in terms of routing, this is a little bit different from what you see in shortest path routing, for example, in OSPF. What you're trying to find here is a primary path and a backup path, and you're trying to minimize the cost of the primary and backup path combined. So what might happen that if you, say for example, find the shortest path as your primary path, and remember you have to make your backup path kind of link and node disjoint, if not the physical layer risk disjoint from your primary path, the corresponding backup path for your shortest primary path can actually be very long. So you use a different kind of algorithm. We use k-shortest path algorithm. There is another algorithm by Sulballs which kind of does the same thing, where it tries to minimize the joint cost of the primary and the backup path, instead of minimizing the primary first and then finding the backup, which is route disjoint from the primary. Now,
Do you always insist on being disjoint in both nodes and links, or is there a different formulation?
there are different formulations actually. What we do, we call it shared risk group disjoint. So for every link or every node, we associate a risk group. So sometimes you might have links which kind of are sharing common conduits. So it might be between, one between A and B, another between C and D, but they might still share the risk. So in our software, though, you have different combinations you can have. You can have node disjoint, link disjoint, shared risk group disjoint, and sometimes it may not be possible to find paths which are completely shared risk group disjoint. So we have a concept of maximally disjoint, where that is the best you can do, given the network topology you have.
So is it also clear that the capacity has to be reserved on the secondary path permanently? Is that assumed in your model?
That is correct. But what is also assumed is that the two backup paths, I mean, if you look at the example here, right, you have a primary path, say, which is on the top, the green solid line there, and the backup path, which is the dotted line there. And you have another solid red line, which is another primary path. And the corresponding dashed red line, which is the backup path, the dashed green line and the dashed red line can share capacities. And the idea here is that, since the primary paths are not sharing any common link or node, they probably are not going to go down at the same time. So if that condition is true, the corresponding backup paths can share capacity. And that's how you get the sharing and the cost savings. We skip this over. So what we did actually, we took this 12 node 17 link US backbone with average node degree of 2.8, and we got the traffic from our specific customers without getting into the details there. And there was total 66 bidirectional demands. Average demand between POPs in this particular study was about 3 Gbps, and that's kind of what you see in most service provider networks today. And most of the traffic flow between the highest pipe or the biggest pipe flow between New York and San Francisco, and it was about 16 gigabits per second. And the smallest one was in between, I think, Nashville and Denver, which was about 120 megabits per second or something like that. And we assumed 75% year-over-year growth, and we assumed a pricing model also, where every OC192 port on a router cost about 125K, and every OC48 or 2.5 Gbps link cost about 45K.
So those costs are per
port.
per port per year, per month?
No,
per
that's what
per
you pay to buy.
equipment?
Yeah, it's,
Okay.
and if you compare the cost, for the optical switches, the OXCs we built, it's about 35K for an OC192 port, and it's about 10K for an OC48 or 2.5 Gbps port. So you can clearly see that optical switches are much cheaper. So if you can take the routers off the transient traffic path, you can actually save a lot of money. And we consider different scenarios. The first scenario we considered is that we compared two models. In one model, you have IP routers connected directly over unprotected WDM links, which is what people are doing today, right? And the second model is where IP routers are connected over shared mesh-protected optical links. So the difference is that in one case you have unprotected links, another case you have protected links, but unlike what people used to do a couple of years back with sonnet protection, you have an optical mesh protection, right? And we ran both networks at 50% utilization. Actually, by the way, most of the IP networks today run at 30% utilization or lower. And service providers don't want to spike it up to 80%. And the reason being the control traffic and the data traffic in the IP domain kind of rides on the same link. So if the network utilization goes very high and 80% is considered to be very high, then you might actually lose a lot of control packets like routing update packets or signaling packets, and that will affect the performance of the network severely. So 50%, although it kind of looks pretty low from when you do network analysis, it's actually pretty high. And what we have assumed in this case is that even though you keep your network utilization at 50%, in one case it is protected, in another case it is unprotected. And if you look at the numbers here, what it shows is that in the first case, when you have IP riding directly over WDM, in year one, let's consider that scenario, you have about 2,000 OC48 router ports which are being used in the whole network. if you look at the second scenario where you have traffic actually going over an optical switched optical network, the number of router ports come down from 2096 to 1500. And the reason being that you can actually create optical bypasses where you can take the transit traffic off the router and put it on the optical backbone. Right? So what happens really is that you are reducing the number of router ports, but you are adding additional optical switch ports. But given that optical switch ports are much cheaper, your total network cost actually goes down, or actually remains pretty much the same. If you look at this in dollar figures, so in one case, year one, when you have unprotected WDM link, the total cost of the network is 87 million, and the cost is 95 million when it is going over optically protected link. So the point of this message is that even if you want to protect your transport network to make sure that a fiber cut does not affect your network performance very much, and even if you assume that you are running the network at the same utilization point, you really don't have to pay so much. It's actually 5% increase in your network cost to protect your transport network, and which is probably a very good investment because it's going to make your network a lot more stable and reliable. Now, what will actually happen is that if you protect your network, it's possible to run it at a higher utilization compared to when you have network which is running where the links are not protected. The reason being that in the first case, when you have unprotected links, if you have a network failure, you need extra capacity in your network so that you can absorb the surge in network traffic on the backup paths. If you have a protected link, you don't have that problem. So in this particular case, the study actually shows, let's assume that the present mode of operation, that is IP over WDM, is running at 30% utilization. And because of the fact in IP over OTN where you have protected the links, you are running it at a higher utilization because you don't have to take care of your link cuts. And if you look in this case and go down directly to the dollar figures here, you save 18% in terms of your network cost. Okay, so coming back to the conclusion here is that if you assume that by protecting the links you'll still run at the same utilization, you don't have to pay so much of money, it's only 5% of your total cost. If you assume it will actually increase your utilization, you can actually save money and have a more stable network. Now, the previous example I showed, we kind of compared the network cost when in one case you are doing IP rerouting, another case you are doing optical layer protection with IP rerouting. The similar comparison can be made when you are using Mpls to protect your network. And without getting into, actually, how much time do I have? It's another couple of minutes.
You can go for another 15.
Okay. All right. I'll probably give some time for questions. So we kind of did the same studies where we assume that in one case, in one case we have Mpls protection at the IP layer, and in the other case you have optical protection at the optical layer. And here actually, in this particular study, the traffic model was a little bit different. The starting traffic was half of what we had in the previous case, and the growth was 50%. Other than that, everything else is the same. And if you look at this particular example, and this only considers the core routers, not the access routers, is that if you look at year one, in case of Mpls, you use 732 router ports. The number of router ports go down to 128 when you use optical restoration. But you add the yellow bar there, 686 optical switch ports. Now, why does that happen? If you go back to this picture here, you can clearly see that is that when you go from POP 1 to POP 4 with Mpls protection, in the intermediate nodes you are burning through router ports, right? When you go from POP 1 to POP 4 in the optical mesh protection, you are burning through the optical switch ports. So essentially what you have done, you have moved your transit traffic from your IP backbone to your optical backbone. And since your optical bandwidth is a lot cheaper than your IP bandwidth, you are saving money. Although you might actually use a little bit more number of ports. So if you go to network cost savings, and by the way, this is only for the core routers. We didn't consider the access routers in this case because they are the same in both scenarios. You save 54% in terms of your network cost because you are essentially, did an optical bypass of your transit traffic and moved it from IP layer to optical layer. So, couple of other reasons why a switched optical backbone might actually be a good thing for you to have, and this is what a lot of people are moving into these days, is that if you have a switched optical layer, like using our switches or switches of Sienna or other vendors, you can move around your wavelengths very quickly. With a point and click, you can move your circuits around. So that's very effective because if you have a big disaster and you want to rearrange your network, it's harder to do when you have your WDM connected routers because it's not very easy to move them around. Other thing is that a lot of this planning and projection depends on how accurate your estimation is. And it's very difficult to actually estimate IP traffic. And it changes pretty often also, sometimes because of changes in application mix, sometimes because of changes in the peering policy one service provider has with another service provider. So if you have a little bit more flexibility, it kind of takes some of the risk out of your equation because even though you might make a mistake while building the network, you can quickly change it around, which is not very easy to do if you have a very static network. So going to, this is good, but what more can we do? I guess a lot of people here are interested in doing some work in IP and IP traffic engineering and things like that. So if you look at research issues and what is happening in IP networks and how people are spending time, the IGP or the interior gateway protocol like OSPF and ISIS, they are very primitive in many ways. I mean, only thing you can figure out how many links you have, who is connected to whom. There is not much information about, what is the capacity of this link, how much of it is really occupied, what is the utilization of the network. So some of that work is happening in IETF and other standard setting bodies and also in the research organizations. What hasn't happened very well though is that because of scalability, OSPF kind of divides the network in multiple areas. You have a backbone area, which is area 0, and then you have other areas connected to the backbone area. So there is a lot of traffic engineering extensions to routing protocols which have been done in the context of a single area. There is some work which has been done when you go from single area to multiple area. But that work is still in its infancy and a lot of work needs to be done before we can go to traffic engineering across areas. The real problem here is that when you go from one area to another, you need to summarize the information. You cannot broadcast that information across the whole network because that's not scalable. But when you summarize that information, you lose a lot of details about your traffic engineering data. So how do you summarize without losing that information is still an open problem. There are other things which are kind of interesting in the context of IP networks is that when IP was designed, nobody really cared about primary path and backup path. You had the shortest path, which was essentially the primary path. Now, if you have both primary and backup paths now, and you want to make sure the primary paths and backup paths are risk disjoint, that they are not sharing the same physical resources, that part needs to be added to protocols like OSPF and at some point in time maybe BGP. So that is still an open issue and a lot of people working on that. There's some work going on constraint-based shortest path first routing, which is essentially extension of SPF, which is used in OSPF and ISIS. In terms of reliability, there are a lot of things that's happening, and one of the interesting problems I see is the fast convergence of routing protocol. So if something bad happens in your network, how do you make sure everybody in the network knows that quickly and finds a way to work around it? So if OSPF can converge in milliseconds, that will solve a lot of the routing problems in the internet, and people are working on that. And that's actually, there are a couple of other things we can discuss later. If you look at optical networks, although not too much work is done on optical network, it's actually a big business. It's a much bigger business than IP business. And what is happening in optical networks is that people are trying to, most of the optical networks are managed from a centralized management system. So you have what is called an element management system or a network management system controlling the optical network. People are moving towards a more distributed and dynamic architecture where you have extension of MPLS known as generalized MPLS, which will do similar things which you see in IP networks. That is, the optical switches will automatically discover their neighbors, they'll automatically discover the topology of the network, and they'll be automatically able to set up light paths when you ask, set up a light path from point A to point B. Other thing that is happening is mesh restoration. I mean, we have a protocol which is run in our switches, which is a proprietary protocol. There's a lot of work going on in standard bodies to have a standard-based protocol which will do shared mesh restoration, which is not an easy task, and there are some extensions to GMPLS to do that. And IP optical convergence is another hot topic in many areas. People are trying to figure out that if the same protocols like MPLS or the generalized version of that is running in both at the IP layer and at the optical layer, what can we do to take advantage of this synergy? Is it possible to automate some of the processes? Like, for example, if a link between two routers go down, can you dial up a backup link automatically without manual intervention? So optical UNI kind of is supposed to do that job. And event-driven network reconfiguration, for example, when traffic goes up a certain level, or based on some application needs. For example, there are a lot of storage area network applications where people need an OC48 for 2 hours every night to do their backups. So you can share your capacity across multiple clients and do the job in a scheduled, basis where nobody will actually set up the link, but it will automatically set it up from certain point in time to certain other point in time.
So for that type of application, what is the driver for that to happen directly over optical rather than as an IP service?
Well, it can happen over IP service also. One of the reasons actually is kind of difficult to do it on IP service is that the latency requirement for protocols like fiber channel or SCON is very low. And it's easier to do it over optical network than over IP network. But even if you do it on IP networks, ultimately you have to have a physical connectivity, right? So optics have to be involved at some point in time. So that's pretty much it actually. And if you have any questions, I'll be happy to answer. Yeah.
What exactly do you mean by event-driven network? Is it that's what you described as the
Right. I mean, for example, this is a practical example. There's a lot of banks in, say, Manhattan, right? They have their data centers in New Jersey.
Mm-hmm.
And every night they do their backups. And these backups are gigabytes per second, right?
Mm-hmm.
So.
Yeah, that's clear. So you don't mean but these events are pretty slow, and they're predetermined.
Yeah. I mean, a lot of people talk about setting up this OC48 or OC192 light paths in seconds, but that's probably not necessary because I don't see any application. It's not like a phone call that you can make it any time. It's pretty, you don't suddenly need an OC48. Okay, yeah, go ahead.
My question is this: you mentioned there they have a failure rate, something like mean time to failure, something like that. Do you have a measure of the degree of the failure? So some failures kind of regional access router, some is more serious, like the very important router. So whether the failure in your whatever the model, whether they are the same or different.
No, I think service providers do have very detailed information about the failure pattern, but they don't like to give it out because they don't want to show people the network actually failed and there is some major failure there. But there are actually detailed information about that. And one way of measuring that would be how many BGP routes, for example, you had to withdraw because of a failure.
The other question is whether you offer the same capacity for the primary and backup.
In optical routing, it is the same capacity. In MPLS, you might actually reserve a little bit less capacity on your backup path.
Then the question is like following. If I assume that the New York City and San Francisco, you mentioned the 16 giga, so the rate is pretty high, and then when you do your calculation, you base it on the 50% of load. And then the thing is, if I knock one arm of the San Francisco has 3 arms according to your plot,
Right.
and then if I knock one of them out, it seems to me like you're gonna increase the other 2 arms maybe around 80%, and then you say this one is maybe very harmful. So is that a problem, or?
Well, I mean,
Yeah. So
you know,
just-
you can do your planning in such a way that in the worst case, your utilization will be bounded by a certain number. And in fact, most of the plannings is done that way, and the worst case utilization is 80%, right? So as long as you have a backup path, you can add enough capacity on that path to make sure that the utilization does not go beyond, you know, whatever percentage you think is appropriate.
So in some of the cost studies you didn't account for the cost of the fiber itself, but then bandwidth cost.
We didn't actually account for the fiber. Fiber cost is, you know, that's already sunk cost and people don't care so much about it. We did compute the WDM cost. And I kind of took it out of this presentation here because they are pretty much the same in both cases, and didn't want to use another variable there. But we have a very sophisticated tool to do this analysis. So we did similar analysis for ATM traffic and other things. Yeah, go ahead.
So did you understand that right? You say you didn't account for the fiber because nobody buys fiber at the moment? There's enough fiber there, and that's it?
It's a sunk cost, right? They already have fiber in ground, and you know they don't care so much about it. And in most cases, actually, you know, you use one strand of fiber, you can now have 160 wavelengths on the same fiber, so it's not that big a cost.
Are there any other questions? If not, thank you.